Welcome to this video on the generic additive manufacturing process chain and file formats. Today we will explore the digital thread that connects CAD design to a final physical part. The digital thread in additive manufacturing represents the complete, step-by-step workflow required to transition from an initial virtual model to a tangible physical object. Phase 1 of the AM process chain begins with CAD modeling to create a 3D design. This model then undergoes tessellation, file repair to ensure it is manifold, and finally, slicing into 2D layers. Phase 2 shifts to execution. This includes toolpath generation, the actual physical build process, removing the part from the build plate, and final post-processing, like heat treatment and inspection. Next, we will look at geometric representation and the file formats that allow computers to store and communicate 3D volume data for additive manufacturing. The STL format is the standard for AM. It uses a triangular mesh and normal vectors to define a solid surface, though it lacks color, material, or scale data. Tessellation involves chordal tolerance. A coarse mesh saves space but causes faceting, while a fine mesh improves surface quality but results in very large file sizes. Common errors in STL files include gaps or holes in the mesh, inverted normals that confuse the slicer, and non-manifold edges where geometry intersects incorrectly. File formats have evolved significantly. Modern formats now support advanced features like multi-material and color data, internal lattices, and embedded machine metadata. Let's dive into slicing fundamentals and toolpaths, which are essential for converting digital models into instructions a machine can actually execute. When slicing, you can choose between constant layer thickness or adaptive slicing. Adaptive slicing varies height based on geometry to balance speed on vertical walls with accuracy on slopes. Toolpath planning involves different strategies, including contour paths for exterior boundaries, raster paths for internal infill, and complex lattices for specialized engineering properties. Finally, process parameters are divided into machine-specific settings, like build volume and kinematics, and material-specific profiles that handle temperature and cooling to ensure structural integrity. For a hands-on exercise, try exporting a complex part with different chordal deviations. Import them into your slicer to observe the effects on faceting and build time. This concludes our video. Thank you for watching this overview of the build cycle, from virtual G-code execution through to the final extraction of your printed part. This concludes our video on the additive manufacturing process chain. Thank you for your attention.